we're going to start by some exercises from sheet 9. Unfortunately, time is tight because there are not many lectures left, so we're only going to spend a little bit of time on the exercises. I'd say let's just do the first exercise of part A. Yeah, because it's good to repeat these properties of our P functions. Okay, so exercise 1 of part A, there were 4 statements, and you should decide whether they're true or false. And the first statement was, okay, so we're given a measure space, P is between 1 and infinity, and then the first statement was if Fn is a bounded sequence in L1, and it converges almost everywhere, then there exists a limit function such that the L1 norm of this difference goes to 0. So in other words, if a sequence is bounded in L1 and converges almost everywhere, then it converges in L1. Is this statement true or false?
Yes, because we showed that LP spaces are Banach spaces, which means they're complete.
Yes, so what? So completeness just means Cauchy sequences converge. But all we know about this sequence is that it's bounded. So its L1 norm is bounded in N. And it converges almost everywhere. But that's different from being a Cauchy sequence in the L1 norm, right?
If we consider Fn equal to n times the characteristic function of the interval 0, 1 over n, we have that Fn goes to 0 almost everywhere, but the L1 norm is equal to 1. So it's not true.
Yes, that's right. Yeah, you still have to argue why there's no limit function, but yes, that's fine. So the statement is false, and the counterexample is the right one. So if you take Fn to be n times the characteristic function of the interval from 0 to 1 over n, so this function looks like this. Yeah, so it starts with a constant 1, and then it's 2 times characteristic function between 0 and 1/2, and so on. So the area under the curve is always equal to 1. So the L1 norm of these Fn is always equal to 1. And the sequence converges to 0 almost everywhere, right? Because if we pick any x in the interval from 0 to 1, then there will always be an n such that this point where the function becomes 0 is to the left of this x. So for every x, eventually f of x will be 0. So the function converges to 0 pointwise. And now, does there exist a limit function? We have to show that there exists no limit function such that the difference of the L1 norm, the L1 norm of the difference goes to 0. So how can we do this?
We call our f is 0, right? Because it's the limit of Fn. And it's not true that the L1 norm of Fn goes to 0 because the L1 norm is equal to 1 for every n.
That's essentially right. I mean, in principle, there could still be a different f, right? Such that the L1 norm of Fn minus f goes to 0.
Yeah.
The L1 limit, in theory, could be different from the pointwise limit. So we have to show that it can't. One way to do this would be to say, okay, assume there exists an f such that this difference goes to 0. Then we know that there exists a subsequence of Fn, right, that converges pointwise almost everywhere to f. But pointwise it converges to 0. So f would have to be 0 if it existed. But then this is impossible because the L1 norm is always 1 of Fn. So let's write this down. Okay, so assume for contradiction that there is such an f, such an L1 limit, then there would exist a subsequence Fnk, which converges pointwise to f almost everywhere. But Fnk converges to 0 by construction. So f would have to be 0. But then we would have the following. The L1 norm of Fn can be written as L1 norm of f can be estimated by the L1 norm of f plus the L1 norm of fn minus f, triangle inequality, right? We add and subtract f inside this norm, and then use the triangle inequality. But now this is 0, because f is 0. So this right-hand side is equal to the norm of fn minus f, but this goes to 0 by assumption. So the L1 norm of fn would have to go to 0. But that's not the case, because the L1 norm of the fn is always 1. So we have a contradiction. So there exists no limit function in L1 for this sequence. So this is really a counterexample.
Can I ask?
Yes.
So it's possible that we have a sequence fn that converges to as a function f almost everywhere, pointwise,
Yes.
and converges to some function, different function in L1.
No, just, I mean, by the same argument. You can always make this argument that I made, I think. Because, I mean, here the limit happens to be 0, right? So if the limit is 0, you can always do this argument, right? Where, okay, you show the let's just do it. It's difficult to explain only with words. But you can use the same argument to show that if the sequence converges pointwise and in L1, then the limits have to be the same. Yeah, let's do it over here. So this would be the situation, right, in your question.
Yeah.
Fn converges to f almost everywhere, and the L1 norm of fn minus g goes to 0, and we want to show that f equals g. Right, so we take a subsequence again, which converges pointwise, because the sequence converges in L1, so we can do that. And then we already have the contradiction, don't we? So f and k converges to g almost everywhere, but f and k also converges to f almost everywhere. So f and g have to coincide almost everywhere. So in L1 they're the same. Yeah, so this you can always do. Any other questions? Okay, let me write down part B. so Fn is a sequence in LP, and suppose that for every epsilon there exists an n such that integral Fn minus Fm to the power p d mu is less than epsilon. For all m n larger than n, then there exists an f in LP such that integral Fn minus f to the power p d mu goes to 0. Is it true or is it false? Why?
Just like this completeness.
Yeah, so this is exactly, more or less, it's exactly completeness of LP spaces. Except that this is formulated for the curly LP spaces where we have functions, and not in terms of the new LP spaces where we have equivalence classes of functions. But this statement is precisely equivalent to completeness of LP. Yeah, we can even write down an explicit proof. So we know that Cauchy sequences in LP converge. So if Fn is a Cauchy sequence in the LP space of equivalence classes, then we know that it converges because these LP spaces are complete. This means that there exists a limit equivalence class F in LP such that the L1 norm between this equivalence class of Fn and the equivalence class of F goes to 0. But then by definition of this L1 norm, this is just the pth root of this integral. So this goes to 0 if and only if this goes to 0. So yeah, essentially it's exactly completeness of LP spaces. Any questions? Okay. Okay, statement C. if we have a sequence Fn as in B, so all of this holds, then there exists a measurable function f such that Fn converges to f almost everywhere. Is it true or is it false?
False, because it's true only for subsequences.
Yes. So yeah, essentially we've already talked about this here in this proof. If you have L1 convergence and you want pointwise convergence, then you have to take a subsequence. Does anyone remember the counterexample? I think 2 or 3 lectures ago we've seen a counterexample that showed that you really have to take a subsequence.
Is it this one with the blocks sort of moving along?
Yes. So this bar that sweeps out the interval again and again and becomes more and more narrow. That was the counterexample. So Fn could look like this bar which moves across the interval and then becomes narrower and then again moves along the interval. That's a sequence which converges to 0 in L1, but not pointwise anywhere. And D, okay, I don't think we have to do part D, because part D just says if you have a sequence Fn as in B, then there exists a subsequence which converges pointwise. But we've said this so many times now and used it already that yes. So part D is true. If you take a subsequence, you can get pointwise convergence almost everywhere. Okay, so this was a reminder of convergence in LP spaces. And now let's carry on with the lecture. So last time we started by introducing product sigma algebra, which was a natural way to introduce a sigma algebra on the Cartesian product of 2 sets. And yeah, this product sigma algebra was defined to be the sigma algebra generated by measurable rectangles, right? So you take sets of the form A times B, where A is measurable in X and B is measurable in Y. And then you take the sigma algebra generated by these kinds of sets, and that we called the product sigma algebra. And yeah, now we'll continue studying this product sigma algebra. So the next lemma is lemma 7.6. Let x comma sigma x comma mu and y comma sigma y comma mu be sigma finite measure spaces. And let S be an element of the product sigma algebra, sigma x times sigma y. Then define Sx to be or y in y such that the pair x comma y is in S, and Sy. So this X is a subscript, this Y is a superscript. So whenever we write a superscript, we mean this. All points X in X such that the pair X, Y is in S. And these sets are called slices. Because if we have a set S which looks like this, and we take a point X somewhere here, then Sx is precisely the points Y and Y such that the pair X, Y is in X. So this slice would be Sx. And the same in the other direction. If we pick a point Y on the vertical axis, then this set would be Sy. Superscript, sorry. Okay, so that's why these sets are called slices. Okay, so this is the situation, and then the statement of the lemma is then the following three properties hold. First, the function that maps x to nu of Sx is sigma x measurable. Second, a similar statement holds for y, so y maps to mu of Sy is sigma y measurable. And finally, integral nu of Sx d mu of x is the same as integral over y mu of Sy d nu of y. Okay, so for every fixed x, Sx is this slice, so we can apply the measure nu to it, and that gives us a real valued function that depends on x, right? So this is a function, and statement 1 is this function is measurable. And if it's measurable, we can try to integrate it, and then in statement 3, the statement is that if you integrate these two functions, you get the same thing, basically. So first taking mu of a section and then integrating with respect to mu gives the same as first taking mu of a section and then integrating with respect to nu. Okay, and the proof is quite long, but the strategy is familiar, I would say. Yeah, basically we're going to define the family of sets where these three properties hold, and then show that this family of sets is equal to the entire product sigma algebra. So first, these sections as x as y are measurable sets. In their respective spaces by lemma 7.5. That's the last lemma we proved last time about measurability of functions on product spaces. If you take this lemma and you take f equal to the characteristic function of S, and this lemma exactly tells you that these sections are measurable sets. Okay, so they are measurable, so this is just to note that we are actually allowed to apply mu and nu to these sets, right? And now step 1 of the proof is first we assume that mu and nu are finite measures. This will make things easier for us, and later we will remove this assumption. Remember the assumptions of the lemma. In the assumption of the lemma, the two measure spaces have to be sigma finite. So now we'll assume that they're finite, and later we'll generalize the sigma finiteness. So we define the following set, curly D, as all sets in sigma x times sigma y such that these three properties hold. And as I said, the in is to show that D is equal to sigma x times sigma y. Okay, so note that by definition D is a subset of sigma x times sigma y, so we only have to show the other inclusion. Okay. And the first claim we're going to prove is that D contains all measurable rectangles. Right, so the final aim is to show that D contains sigma x times sigma y. The first step is to show that D contains all measurable rectangles, so D contains a generator of these. That's what we're going to show now. So that's a good start. Okay, and to prove this claim, take a measurable rectangle. So let A be a set in sigma x, B be a set in sigma y, and now let's look at the sections, the slices of A times B. So A times B subscript x. If you look at the definition of these slices, then for a rectangle, so for a set of the form a times b, it's easy to see that you get b if x is in A and the empty set otherwise. Right, so if you take the Cartesian product between two sets and you take a slice, then you end up with one of the two sets again, more or less. And the same is true for the other kind of slice, A times B superscript y is A if y is in B and the empty set otherwise. Okay, so for measurable rectangles, these slices are particularly simple. And what do we want to show? We want to show that measurable rectangles are in D, which just means that for measurable rectangles, these three properties hold, right? So we have to show that this function is measurable, this function is measurable, and we have to show this equality of integrals. Okay, so let's take a look at these functions. If we consider nu of such a slice, a times b subscript x, then because of these two things, this is just nu of b times the characteristic function of a at the point x. And similarly, if you apply mu to the other slice, a times b superscript y, you get mu of a times the characteristic function of b at the point y. So these are just multiples of characteristic functions. So in particular, they're simple functions. So in particular, they're measurable. Okay, so 1 and 2 are satisfied already. And because these are simple functions, computing the integral is easy as well. Integral x mu of a times b subscript x d mu of x is just the same as, well, nu of b times the integral of this characteristic function. So this is just nu of b times mu of a, and this is the same as the other integral over y. Mu of a times b y d mu of y. Just because we're integrating these characteristic functions. So these two integrals give the same thing. So point 3 is satisfied too. So in particular, all 3 points are satisfied on measurable rectangles. So all measurable rectangles are contained in this set D. So this proves claim 1. Okay, so now we know that D contains a generator of this product sigma algebra. The next claim we're going to prove is that D is a D system. Okay, to show that D is a D system, we have to check 3 things. First, x times y has to be in D, the entire set x times y. This is true by claim 1, right? Because x times y is a measurable rectangle. So this is clear. Second, to show that D is a D system, we have to show that if S and T are in D, and S is a subset of T, then we have to show that also T minus S is in D, right? So for the set T minus S, these 3 things have to be satisfied, and by assumption S and T are in D, so for S and for T, these 3 things are, we can assume that they're satisfied. So let's look at T minus S. So mu of a slice T minus S x this is the same as mu of the slice Tx minus the slice Sx. Yeah, if you first take the difference and then take the slice, it's the same as first taking the slice and then taking the difference. Yeah, if you look at the definition for 5 minutes, you'll see that this is true. And now, this is a measure applied to a difference of sets. So this is equal to mu of Tx minus mu of Sx. And this equality is true because mu is a finite measure. Remember, if you want to use this formula where you get this set that you subtract with a minus sign, this formula only holds for finite measures, because otherwise it might happen that you get infinity minus infinity. Okay, so here we're using this finiteness assumption that we made at the beginning of step 1. Okay, and now, by assumption, T satisfies these 3 properties and S as well. So this is measurable, and this is measurable, because T and X come from D. And maybe I'll leave these 3 properties on the board. And we can do the same thing for mu. So mu. So this means that a difference between 2 measurable functions is measurable, so this entire thing is measurable. So this first property is satisfied for t minus s. And we can do the same thing for mu. Mu of t minus s superscript y is the same as mu of ty minus sy is the same as mu of ty minus mu of sy. And these two are measurable individually. So the whole thing is measurable. Again, this equality with the minus sign holds because mu is finite. Okay, so t minus s satisfies properties 1 and 2. Now we have to show that t minus s satisfies property 3. So we have to integrate these two functions. And then we have to get the same result. Okay, so the integral on the left-hand side with s replaced by t minus s is integral s mu of t minus s subscript x d mu of x. And now we can use this formula again, right? Nu of this t minus s slice x, we can replace by this difference, nu of tx minus nu of sx. So this integral is the same as integral nu of tx d mu of x minus integral nu of sx d mu of x. And now we can use the fact that t and s satisfy these three properties. So this integral with tx and this integral with sx, we can swap mu and nu because we can use this third property. So each individual integral we can replace by integral y mu of t y d mu of y minus integral y mu of s y d mu of y. And now apply this formula for the difference again, and then this is equal to integral y mu of t minus s y d nu of y. Right, so we've shown that this formula, this integral formula holds for t minus s. So we've shown the entire set is in D. We've shown that if S is a subset of T and they're both in D, then T minus S is in D. And then there's one thing missing for D to be a D system. Let me just conclude this second point. So this integral formula shows that 1, 2, 3 hold for t minus s, so t minus s is in D. Okay, and the next point to show that D is a D system is if we have a sequence of increasing sets, and each of these sets is in D, then the union has to be in D. Okay, so let's take an increasing sequence of sets in D, and let S denote the union of all these. Then what we have to show is that S is in D. In other words, S satisfies these properties 1, 2, 3. Okay, so first, for every x in X and y in Y, we have that the slices of Sn at X, they're also an increasing sequence of sets, and they converge from below to Sx, which means that the union of these slices is equal to the slice of S. And the same is true for Y. And this implies that nu of Sn x as a function of X, this converges from below to nu of Sx, and mu of Sn y converges from below to mu of Sy. Right, so these are sets which converge monotonically, which grow, and on the right hand side these are functions of X and Y. Because these sets are increasing, the functions are also increasing. And we have these two monotone convergences. And this right hand side holds because of the monotone convergence theorem for sets. Right? If you the nu applied to the union of all these Sn x can be written as the limit of the nu of the individual Sn x. So this right hand side follows by the monotone convergence theorem for sets. Okay, now we have monotone sequences of functions. So first of all, because these two functions, nu of Sx and mu of Sy, because these are pointwise limits of measurable functions, they themselves are measurable functions. So x maps to mu of Sn x, and y maps to mu of Sn y are measurable. Again, because these are limits, sorry, there's no n. Mu of Sx and mu of Sy. They are measurable because they are limits of measurable functions. And now, okay, so these are measurable, so these first 2 points are satisfied already for S. And now we look at the integrals again. So integral x nu of Sn x d mu of x. We know that this is the same as integral y mu of Sn y d mu of y. That's by assumption, because Sn came from d. So for each individual Sn, this integral formula holds. Okay, and now what we want to do is take n to infinity on both sides of the equation, and then conclude that the same equation is true for S. And I mean, look what we have. This is a non-negative function for every n. This is a non-negative function for every n. In n, this is an increasing sequence. This is an increasing sequence. So we can apply the monotone convergence theorem to both sides. So if we take n to infinity, we know that the integral on the left-hand side converges to the integral of nu of Sx, and the integral on the right-hand side converges to the integral of mu of Sy. So taking n to infinity, we conclude that integral nu of Sx d mu of x. So this is the limit of the left-hand side. This has to be equal to the limit of the right-hand side, which is integral mu of Sy d mu of y. And this holds because of the monotone convergence theorem. Okay, so the integral formula holds for S. So point 3 is true for S. So S is in D. So so claim 2 is proved. Okay, now let's recall what do we have. We proved our first claim, which was that D contains all measurable rectangles, and we proved our second claim, which was that D is a D system. Okay, measurable rectangles are a pi system, right? If you take the intersection of two rectangles, it's a rectangle again. So D is a D system which contains the pi system of measurable rectangles. So we can apply Dynkin's lemma. To the pi system of measurable rectangles. And from that we get that the sigma algebra generated by A, which is the product sigma algebra by definition, this is equal to the D system generated by A. So this equality is Dynkin's lemma. Okay, but we just proved that this set D is a D system that contains A. So the D system generated by A must be a subset of D. But now look what this is. This line says that the product sigma algebra is a subset of D, which is precisely what we wanted to prove when we started the proof, right? Down here I wrote aim, prove that D is equal to the product sigma algebra. And when we wrote down the definition of D, we noted that D is a subset of this by definition, so we only had to prove the other inclusion. So now this is done. So let's maybe write, but D is a subset of sigma x times sigma y by definition. So D is equal to sigma x times sigma y, and D being equal to sigma x times sigma y precisely means that these three properties hold for every s in sigma x times sigma y, which was the statement of the lemma. So now we are almost done with the proof, because at the very beginning of the proof we assumed that the measures are finite. And we want to prove the statement for only sigma finite measure spaces. So this is step 2, and I'm only going to sketch step 2 because the proof is really long already and the hard work is already done. So step 2, I think I can erase this. Step 2, mu of x and mu of x, mu of y, sorry, can be infinite. Well, what you do is you write x as an infinite union of sets xn with finite measure, and the same for y. Then for some generic set S in x times y, I mean for some set in the product sigma algebra of S x times y, you can apply step 1 to the set S intersected with xn times yn. Now this is a bounded set. This set is a set of finite measure. This intersection to this you can apply step 1. And then these properties 1, 2, 3 hold for subsets, and then you can use the monotone convergence theorem again to show that these three properties still hold if you take n to infinity. So this is in a nutshell how you generalize this to sigma finite measure spaces. Okay, and I think now it's time to take a break. And yeah, we continue in 10 minutes.
Yeah, alright. I'm at the stage where I can't really do it.
How much do you think you're going to do over Christmas?
Everything's written out properly. So I've kind of done a rough
Yeah.
draft.
It's going to be like, I'm not going to do much. I'll carry on reading.
I'm going to try and
But
do some new stuff.
I don't mind neglecting it for like a week or two.
What measure?
No.
Definitely don't want to catch measure food, but
I'm going to neglect my theory over Christmas.
Yeah, right.
just start revision a few days before the exam.
When's Friday night? We have to start after Friday night.
Oh god.
No, I can't do that. Like, I'd like to think I could, but I physically can't do that.
Yeah.
I end up being sick and stuff.
Yeah.
Or I actually did that. It would be like, yeah.
That's pleasant.
It's actually like that's probably a common nightmare of mine.
What?
Waking up in the middle of the night. Oh god, I haven't done any work.
Yeah.
It's one of those like, people, that's what I'm truly scared of.
Yeah, no, this is-
Like the worst thing that can happen is like go into a coma for the last like month.
Yeah.
Then but I still have to sit exactly.
Yeah.
That's actually my worst nightmare.
Yeah. Worst nightmare is not doing enough work.
Yeah. But before,
More
well, actually, I
and
tell you
more.
what, a coma would do me nicely. Nice bit of rest.
My night
Yeah.
sleep, my sleep is
It's
getting
like
more and
24
more
hours. 24-hour coma would be great.
You probably lose a lot of weight as well.
Yeah.
I guess you do lose weight in coma.
They hook you up to like fluids and stuff, then
That's the design. That's the new diet.
put yourself in
The
coma.
coma. Yes, well, hibernation, isn't it?
You get some treatment head as a hammer.
Yeah, but you do it in such a way that it will be killed or have really lasting effect.
Yeah. Just enough to keep you in a coma.
Yeah.
What about a small vehicle?
Like a tap tap.
Or a golf cart. No.
It's good then.
My sleep is getting terrible.
Oh, I can't remember the last time I went to bed before 2.
I got out for 2 hours of sleep last night.
You gaming?
No, I wasn't. I got back because I went rock climbing yesterday. It's down bouldered. So I got back there.
Did you boulder or do you rock climb?
I went rock I tried bouldering as well.
There's a good place in Newport for that. But it's like I don't like falling.
Bouldering's
Yeah.
probably not for you.
No, but it's good fun though.
Oh, I had an instructor for the rock climbing. He said he went bouldering a few months ago. He broke his ribs bouldering because it is much more dangerous because there's no safety equipment.
Well, it's like, especially if you've done a lot of rock climbing and you're like, oh, don't worry, it doesn't matter if I fall.
Yeah.
Yeah, I got back at 9.
That's how you can get that coma you're looking for.
Immediately tried sleeping, could not. Woke up usually 6 or 7 times in the night. No, I was genuinely just trying to sleep. Worse now.
I just keep getting woken up when you go to the toilet. This prostatic hyperplasia thing. You know, I'm getting old now. An all-nighter to me means can I make it through the entire night without getting to the toilet?
You just have like a bucket under your bed.
Yeah, bedpan.
Did it, you were 70 something.
Yeah.
Okay.
Between waking up in a cold sweat, you know, thinking of the exams and
I think it's just getting I'm just ready to start the holidays, just like nuts down my vision full
Yeah.
time.
this is what week we're in. Yeah, last week. Next week is like just scrap next week. Stuff.
What did we do? What did we find out on Wednesday? you finish the exam, which is
That's what I'm trying to remember.
January. What's it called? No. October.
Oh yeah, we basically just did that example with diagonal.
what, in 2 hours?
Yeah. There was a question after it, which we still had to do it, so we did the diagonal thing.
I hope I can actually do it when it comes to doing it.
What, the exam?
Yeah.
You've looked through the past papers, you know what sort of
I
questions.
know what's going to come up, I just don't know how to solve any of the problems.
Is this finished?
Yeah.
That's why I put repetition as a form of answer.
Pardon?
Repetition.
Yeah. I could just see the solution to last year's.
What I'll say, if they are repetitive, at least you can answer them quickly, and thus, if you do find that you're struggling with them, you've got more time.
They are all 3 hour
All time to
papers,
sweat
aren't
because I have no idea what I'm doing. I can't possibly derive it from scratch because there's absolutely no way to do that whatsoever.
The worst thing is if you ask for like a random definition or something, maybe.
Random definition.
I mean, they've
okay
had
with
to
that.
define necking instability quite a bit.
Definitions effectively are all there is in a module.
Infinite.
There's no derivation. There's like
She just now
Go 2 proofs.
yeah, 2 proofs.
She flew over them.
What's it? Polar decomposition inheritance.
And the other thing.
They're all swinging for that course.
The spectral one.
Yeah, and that's probably 5,
There was
honestly.
Yeah, that's what I said.
Yeah.
We've heard all about page
2016. Oh.
Bread. I'm gonna make some sandwiches. I'm gonna make bacon free honey chutney.
No,
One sandwich.
For dinner.
Yeah. I'm gonna make
I'm not sure.
like fried egg, bacon, cress, market.
And then
Good combination.
Sweet potato, feta, that being enchiladas.
Ooh, I like
she
those.
does find out.
They're very good.
Are they like ones you made or?
Yeah.
Nice.
So it's just trying to find vegetarian recipes. So many.
Yeah,
vegetarian.
she does,
I'm not a pescatarian. My girlfriend's vegetarian.
I think when
I can't actually just eat fun to fill without doing a meal with her.
I think I can't remember his name now.
We discovered my love for fish fingers.
But one of the PhDs did it.
Was it Will who said you could go home and have a fish sandwich? Yeah. And on that day, I was like, you know what, I
Yeah,
really
it's
want
yeah,
out.
fish fingers.
I had one.
The one who's there, like, yeah. Oh yeah.
Such good street food, can you combine like 20
Yeah.
Yeah.
fish fingers?
They feel so rejuvenating. Such omega-3 much wow.
Brings me back.
Imagine putting a breaded item on bread.
Yeah.
You guys are
Only discussed in cheese.
Yeah, that's it. Make it look
Get your tree off.
What, bacon?
Pasta beans and cheese, yeah.
What, big, oh, no.
It's like
It seems like
that's
it's
like
fantastic.
a measure.
Singing the beans as pasta sauce.
Wait, what's pasta
That
sauce?
would be a
Wow. That's so weird.
As a student,
That's
as
a
a
classic Heinz business going on.
Please,
Sounds quite good. Yeah.
He's sponsored.
It's like deceptively good.
Oh, I'm ashamed to say I had a pizza the other day.
You had
really
one?
loved it.
That's sometimes quite good.
I had a pizza base, I didn't have much in the fridge. So I decided to bake beans and cheese.
Nah, that was quite good.
That's
Yeah,
actually quite good.
I've had that one.
It was alright.
Frankie and Benny used to sell that.
Really?
Yeah. It was really good.
I think I got the bean cheese balance pretty well.
Good.
So.
I might try that sometime. Pizza base,
God,
beans, cheese, it's pretty easy.
God, I'm scared to like actually have to cook proper things in the future. What's in the fridge? Put it all together. Oh, because last week now, before I go home, I was like, use everything in the fridge. I wonder what.
I won't
Well,
struggle
one, I
with
wonder
using up
what.
everything in my
Well, one,
fridge.
one, I wonder what's gone off and developed a new life form.
Yeah.
I'm pretty sure there's like a packet of grapes I've neglected since like
Oh,
October. I'm just scared to look
Cool.
at.
Buy some
Okay,
berries.
let's continue.
And then just never eat them. And then a bit of vitamin C.
Okay, so this lemma with the long proof that we just proved allows us to make the following definition. Let x, sigma x, mu, and y, comma, sigma y, comma, mu be sigma finite measure spaces. Then the product measure of mu and nu, and we denote this by mu times nu, is on the product sigma algebra x times y, comma, sigma x times sigma y is defined as mu times nu of the set S is equal to the integral over x nu of S x d nu of x, which is the same as integral y mu of sy d nu of y. So this is how we define the product measure of a set in x times y. And by lemma 7.6, which we just proved, this is well defined, right? These two integrals are actually the same thing. Okay, so because of this lemma, this is actually a natural thing to define on a product space. And we're going to move on and study integrals with respect to this measure mu times nu. But first, we want to convince ourselves that this really defines a measure. So proposition 7.8 says that this thing actually defines a measure. X, comma, sigma x, comma, mu, y, comma, sigma y, comma, nu, sigma finite measure spaces. Then mu times nu is a measure. And the proof is not too difficult. We have to check three things. First, mu times nu must be always non-negative, but that's clear from the definition because it's defined as an integral over a non-negative function, so it's always non-negative. Similarly, if you plug in the empty set, you have to get 0. That's also clear from the definition. Because if you plug in the empty set, then any section, any slice at any x gives the empty set. So you just integrate 0 so you get 0. And the only non-trivial thing is countable additivity. So if we have a sequence of sets Sn in the product sigma algebra, which are disjoint, and we let S denote their union, then we have to show that mu times nu is additive. So if we want to use the definition of mu times nu, we have to take these slices. And if these sets are disjoint, then the sets of slices are also disjoint. So the S and the sequence of S and X are disjoint. And the slice of S is the union of all slices of the Sn. And with this, we can go to the definition, plug in the Sn, and then it basically follows from the monotone convergence theorem. So by definition, mu times nu of S, the union, is integral x mu of the slice as x d mu of x, which is equal to, we know that nu is a measure, and we have this union, this disjoint union that gives Sx. So nu of Sx can be replaced by the infinite sum of nu of Sn x. Okay, so this step follows just because nu is a measure. And now we want to swap the sum and the integral, and that we can do by the monotone convergence theorem. Because this infinite series, because all of these mu of Sn are non-negative functions, this series is the limit of an increasing sequence of functions. So to this we can apply the monotone convergence theorem and then swap the sum and the integral. And now this is it. So by definition, this integral inside the sum is just mu times nu applied to Sn. So we have exactly this countable additivity formula that we wanted to prove. And that's it. So this proves that mu times nu is actually a measure. Are there any questions? If not, then we have one remark. Saying that sigma finiteness is actually important. So in all of these statements, we assume sigma finiteness of the measure spaces. The first time in lemma 7.6, the one with the long proof. And sigma finiteness is in fact crucial. And in the lecture notes you'll find a counterexample. In the lecture notes there's a counterexample that shows that lemma 7.6 is in fact wrong if you don't assume sigma finiteness. So this equality between these two things is not necessarily true. So in other words, if the measure spaces are not sigma finite, it's not clear how to define a product measure. It's only natural on sigma finite measure spaces. Okay, and then one quick example for a measure which is not a product measure. You can do the following. You can define a measure mu on the Borel sigma algebra of the real numbers times, again, Borel sigma algebra on the real numbers. You can define a measure by mu of S equals integral chi s of x comma x dm of x, where m is the Lebesgue measure. Then this measure cannot be expressed as a product measure of two measures. And again, we don't really have time to do this on a blackboard, so the proof of this is in the lecture notes. So this concludes this first subsection. So we defined product sigma algebras, we defined a product measure, and in this next subsection we will study integrals with respect to this product measure that we just defined. This section is called Iterated Integrals, and it deals with the following question. When do we have integral x, integral y, f of x, y, d mu of x, d mu of y equals integral y, integral x, f of x, y, d mu of y, d mu of x. Right, so if I have two measure spaces, then I can look at the product of these two spaces. And if I have a function on this product space, then I can either write down this integral where I first integrate with respect to mu and then with respect to nu, or I can swap the order of integration. Sorry, this x and y was the wrong way around. Okay. Or I can swap the order of integration and first integrate with respect to nu and then with respect to mu. And then of course it's interesting whether you get the same thing in these two cases. And in addition, these integrals, I've just written them down ad hoc, and it would be interesting to know what the relation is between these integrals and the integral with respect to this product measure that we defined. So the next question would be, how do these double integrals relate to the integral over x times y f d mu times nu. So these are the questions that this section will answer. And to make this more explicit, we start with an example. So if we look at the following function, y squared on R2, y squared minus x squared divided by x squared plus y squared squared, then if we take this function and we integrate it from 0 to 1 first with respect to x, and then from 0 to 1 with respect to y, if you do this, you get pi over 4. If you take the same function integrated from 0 to 1 first with respect to y and then with respect to x, get minus pi over 4. So for this particular function, the order of integration actually matters. You get different things whether you integrate first in x, then in y, or first in y, then in x. And the question is now, why is this? What's so special about this this function? Because I mean, it looks completely benign, right? It's a quotient of polynomials. It's not really a complicated thing. Yeah. So one question would be, why do we get different things? And perhaps more interestingly, how can we avoid this? How can we make sure that the order of integration does not matter and we get the same thing? Which assumptions do we have to make about the function? And that's precisely what the next theorem does, and it's called Tonelli's theorem. So the statement of the theorem is this: let x, comma, sigma x, comma, mu, and y, comma, sigma y, comma, nu be sigma finite measure spaces if we have a function f from x times y to the non-negative real line, which is a product measurable. So if f is sigma x times sigma y measurable, then the function that maps y to integral f of x y d mu of x, and the function that maps x to integral f of x y d mu of y. These functions are both measurable. So the first one is sigma y measurable, and the second one is sigma x measurable. And the following formula holds: integral over x times y f d mu times nu. So this is the integral with respect to the product measure that we just defined. This is equal to integral over x integral over y f of x comma y d nu of y d mu of x, and this is equal to the other double integral where we swap the order of integration. Integral y integral x f of x comma y d mu of x d mu of y. So this is the statement of the theorem. Maybe before we prove it, so if you look at this theorem, this the statement is precisely what we want, right? This theorem gives a condition, okay, if all of this is satisfied, then the order of integration does not matter. We can integrate this way or this way, and we get the same result. And the result is even the same as the integral with respect to the product measure that we defined earlier. So, quick sanity check. What goes wrong in this example? Which of the assumptions of the theorem are not satisfied in this example?
Non-negative.
That's correct. There's a minus in front of the x squared, so this function can become negative. And in fact, for this function, even the integral is negative. So this function is not non-negative. But non-negativity was one of the assumptions in the theorem. So yeah, there's no contradiction between this example and this theorem. And in the proof, you will see that this non-negativity is important for the proof. Without it, yeah, we wouldn't know what to do. So, yeah. To prove this, start with a simple case. If f happens to be a characteristic function, so a characteristic function of a set in the product sigma algebra then this statement of the theorem is exactly the statement of lemma 7.6, the lemma that showed that the definition of the product measure was well defined in the first place. Okay, so for characteristic functions, there's nothing to prove. But now, because all the statements are about measurable functions, and because integrals are linear, immediately the theorem holds for simple functions also, right? If it holds for characteristic functions, we can multiply them by numbers and we can add them, and that's not going to destroy measurability, and it's not going to spoil these equations, because integrals are linear. So adding and multiplying by numbers, that doesn't spoil anything. So immediately, because it holds for characteristic functions, it also holds for simple functions. Okay, so this we get for free. And now take a measurable function. Let f from x times y to 0 infinity be product measurable. So measurable with respect to sigma x times sigma y. Then, just by measurability, we know that there exists a sequence of simple functions which is increasing and converges to f pointwise. That's theorem 4.13. That gives us this increasing sequence of simple functions. And now we can take this this increasing sequence and apply the monotone convergence theorem. get that the integral over y fn of xy d nu of y converges from below to the integral over y f of xy d nu of y, and the same for the integral over x fn of xy d mu of x converges to the integral over x f of xy d nu of y. And the first statement is true for every fixed x in x, and the second is true for every fixed y in y. Right? So just if we look at this first line, we consider these fn as a function of y. We keep x fixed, and then to that function, to that sequence of functions, we apply the monotone convergence theorem, and we get this convergence of integrals over y. And in the second line, we keep y fixed and consider fn as a function of x, and apply the monotone convergence theorem to that. And this gives us these two convergences of integrals.
Should it be mu of x when you're getting mu of y on the bottom line?
Yes, it should. Thank you. Okay, so in particular, this right-hand side is the limit of a sequence of measurable functions, because these are integrals of simple functions are again simple functions. So, because these integrals are pointwise limits of measurable functions, they themselves are measurable. So these two statements follow from these two lines. I gave numbers to these equations. So this is 1, this is 2, this is 3. So from the monotone convergence theorem, we get 1 and 2. And then 3 follows by applying the monotone convergence theorem again to the double integrals. 3 follows by applying monotone convergence theorem again to the double integrals integral x, integral y, fn of xy du of y, and integral fn of x, y